In this tutorial, I'm going to show you how to use the new EELS standards feature in elemental analysis to use experimental references for elemental mapping. The sample we're looking at this time is a semiconductor device, so there are lots of different elements and very well separated phases. I have a dual EELS dataset open. Right now, we are looking at the ADF image and the low loss and high loss EELS spectrum images. I'm already in the analytical technique. We can go ahead and expand the elemental quantification palette and select the high loss spectrum image. The quantification list is already populated as I created a saved analytical setup earlier to save some time. Analytical setups can be loaded by clicking on the folder button in the elemental quantification palette, choosing a setup from the list and clicking OK. All of the edge setup parameters for the elements in this list are default settings using Hartree-Slater cross-section models. Next, click on the Map button. For this sample, signal integral maps make the most sense. We want scale by cross-section enabled. No changes are needed to the settings, so I'll just click OK to generate some maps. The model-based quantification algorithm has generated us some good-looking high signal-to-noise ratio maps. Phase separation has been handled well, even for nitrogen, titanium and oxygen, which are overlapping signals in the spectrum. I'm going to move the tantalum and tungsten maps to the original workspace so we can look at the features in these maps a little more closely. I'm going to use the spectrum picker tool on the high loss dataset to extract spectral data over a group of pixels in a region which I know is a tungsten plug. If I drag this picker ROI out of the image window into the tantalum map, a second mirrored spectrum picker ROI is now present in the tantalum map. As I'm using mirror picker objects, any changes to the position or size are mirrored, so we can easily correlate features in the spectrum image and map with the extracted spectrum. It looks like there is some chemical shift or miscalibration at the tungsten edge, but the Hartree-Slater cross-section shape is quite representative of the data overall. Now look at the fit in the tantalum layer. Here the fit coefficient for the tantalum cross-section model is high, but the shape doesn't quite fit the real edge shape. In fact, the software has incorrectly added in some tungsten, as a combination of the two Hartree-Slater cross-section shapes gives the best fit here. You can see the error in the tungsten map. There is a layer of tungsten in between the two plugs, which isn't real. This is a good example of where using experimental standards instead of calculated cross-sections would help us. As we know the phases here are well separated, I'm going to take references from the dataset itself, or internal references, from regions where I'm confident tungsten and tantalum aren't present together in order to create pure standards for each. Let's measure some standards. First of all, make sure the spectrum picker ROI is in the right place. I'm going to start with the tantalum standard as I just selected a region that I know is pure tantalum. Next, select the tantalum signal in the edge list. Left-click on the small triangle to the bottom right-hand side of the Map button in the elemental quantification palette, and then left-click on the Measure button. Choose an appropriate background window. If our data is dual EELS, we get the option to remove plural scattering from our reference. I want to do this, so I'll click Yes. Next, give the standard a sensible name and add some notes. I like to add the microscope I used for the experiment and state that the data was a sum of multiple pixels from a spectrum image. The last thing to do is to set the energy range of the standard. This parameter is used to define the energy of the splice point used in the quantification. The experimental edge shape is used up to the end of the range and spliced to a modeled cross-section shape above this energy. A good approach is to look at the standard shown and then adjust the range value until we are happy with the fit. Then, click OK and repeat the process for as many other elemental signals as needed. I'm going to repeat the process for tungsten and silicon. Once the standards have been created, I need to check the edge setup. Click on the Sigma button in Elemental Quantification to enter edge setup, which automatically overlays the background and edge signals on the high-loss EELS data. Tungsten, tantalum, and silicon overlap. The software automatically detects this and creates a single fit window. All I need to do is make sure the background window is good over the whole specimen. The background slope is quite different in the tungsten and silicon regions, which is to be expected. I'll reduce the size of the fit window to account for this and improve the overall fit. Before I generate the maps, look at the cross-section model in Edge Setup. The software has automatically chosen the standard I just collected for silicon. If I left-click on the button next to the standard name, I can see the parameters and the notes I just wrote. Let's make the same check for tantalum and tungsten. Finally, I'll plot the intensity maps as before. Now, let's compare tantalum and tungsten again. In the new maps generated using experimental standards, the artifact in the tungsten map is no longer present. This is because the true edge shapes are now represented accurately in the fitting.